This video presents declassified and licensed material of the Global Institute of Logic and Cybernetics.
Modern defense and intelligence frameworks rely entirely on digital networks that cannot fail. Global military infrastructure demands absolute data sovereignty and immediate execution at a massive scale. Legacy Web3 architectures attempt to provide this sovereignty, but contain a mathematical flaw, relying on probabilistic consensus. These systems guess the correct ledger state through voting or energy expenditure, and string those verified transactions into a linear chain. This chart shows ON linear ledger growth, where computational time increases directly with dataset size. As nodes process every previous transaction, validation overhead compounds. The red curve buckles under the data weight. The sheer volume of redundant verification creates a mathematical ceiling, choking the network to single-digit processing speeds. To engineer Web 4.0, we must abandon probabilistic linear chains. The replacement must be deterministic, utilizing geometric network topologies that map data to exact spatial coordinates. A system guaranteed to reach a computational limit cannot support a global economy or an interplanetary logistics network. Linear ledgers are structurally predestined to bottleneck and fail. Processing limits are only the first failure point. A surge in quantum computing power threatens to instantly dismantle the encryption securing these networks. Standard encryption protocols like RSA and ECDSA rely on the difficulty of factoring large integers. Shor's algorithm, a quantum computing function designed specifically to find the prime factors of an integer, performs this task exponentially faster than any classical computer. This graph maps Shor's algorithm efficiency. Operating at O times log n to the third time, the calculation curve slices directly through the maximum defensive thresholds of standard RSA key sizes. Once a quantum processor reaches sufficient qubit stability, encryption taking millennia to break will dissolve in minutes. Digital Fabrica Theory, or DFT, provides a framework designed specifically to bypass these physical scaling limits and cryptographic obsolescence vectors. Relying on increasingly difficult mathematical puzzles is a losing strategy against quantum processing. Security must be anchored in the physical, topological structure of the network itself. At the core of DFT is a mapping system inspired by Eric Weinstein's geometric unity. It structures the network as a 14-dimensional continuous manifold, denoted as M14. A manifold is a topological space that locally resembles flat standard geometry, allowing highly complex structures to be calculated smoothly. This structure embeds different network states directly into the geometry. Dimensions 1 through 3 manage physical spatial locations. 4 through 7 govern topology and connection. 8 through 10 encode governance policies, and 11 through 14 dictate economic parameters. Because navigating a 14-dimensional space directly is impossible for human operators, the system projects this data downward. Users interact with a rigid 2D hexagonal grid, where each hexagon acts as a strict mathematical projection of the higher dimensional space. Smart contracts operating within DFT do not read flat, isolated data points. They execute cross-dimensional reasoning, evaluating physical location, network health, and economic costs simultaneously. This reasoning is formalized mathematically. A contract's decision is calculated as an integral over the manifold's volume, mapping the state of the contract against the specific dimensional gradient it needs to evaluate. By utilizing this math, the network treats abstract constraints, like a minimum token reserve or an ethical voting threshold, as actionable physical slopes within the geometry. Fusing all variables into a single continuous shape eliminates the need for external data oracles. Removing external human input seals off the primary vector for data manipulation. To solve the linear scaling bottleneck discussed earlier, DFT employs a beta scaling protocol. Instead of appending every new transaction to one long chain, localized network hubs, called subnets, autonomously replicate themselves in a deterministic recursive fractal pattern. The expansion is dictated by this set theory equation. When a subnet nears its operational capacity, it generates child subnets, dividing the processing load while maintaining the exact same functional geometry. This growth is strictly governed by a Hausdorff dimension of 1.5. The Hausdorff dimension is a metric used to measure the roughness or fractal complexity of a shape. A value of 1.5 ensures the network fills space efficiently, balancing rapid outward expansion with dense internal connectivity. Because the branching factor is precisely calibrated, the system generates exactly enough capacity to meet real-time demand. This prevents the network from consuming massive amounts of redundant computational power. This architecture shifts the network scaling profile from a linear, O of n, directly to a logarithmic, O of log n. As the system grows exponentially larger, the time required to verify a transaction barely increases. Transactions within these localized subnets are processed entirely independently. A spike in traffic in one sector has zero impact on the validation speeds of another. By replicating its architecture instead of lengthening its chain, the infrastructure supports billions of endpoints globally without a single millisecond of latency degradation. Securing this infinite capacity against Shor's algorithm requires post-quantum lattice-based cryptography. In DFT, cryptographic keys are not merely computed by multiplying primes. They are derived physically, traced through random mathematical walks across dense network structures. The specific topological engine used for this process is a Q+1 regular Ramanujan LPS expander graph. Expander graphs are highly connected sparse graphs that allow rapid traversal between any 2 points. The graph's stability is defined by this spectral gap formula. The spectral gap measures the difference between the two largest eigenvalues in the graph's matrix, determining how quickly data mixes across the network. A massively large spectral gap guarantees optimal node connectivity. It ensures that isolating or partitioning any section of the network requires an impossible amount of energy. Extracting a key from this structure mathematically reduces the decryption attempt to the hidden subgroup problem. Solving this requires analyzing symmetries in complex mathematical groups, a task proven to be entirely quantum hard. Anchoring security to the physical properties of Ramanujan graph walks provides absolute immunity. An attacker cannot simply compute a faster answer. They must physically map an impossibly dense geometry. Even with quantum immunity, decentralized networks collapse from within due to conflicting governance rules or hostile takeovers by hyper-wealthy users. To prevent internal failure, DFT encodes all network policies and governance frameworks strictly as topological knots. Policies act as continuous loops that can be twisted and adjusted, actions known as Reitemeister moves, without ever breaking the base logic. The system runs the Alexander polynomial against the knot's geometry. This specific polynomial calculates invariance, properties that remain unchanged regardless of how the knot is twisted, proving definitively that the policy contains no logical contradictions. With the logic verified, the network must secure its economic balance. To regulate token distribution and voting weight, the system deploys mathematical models originally pioneered by Bernhard Riemann. The architecture uses the Riemann Zeta function. By mapping token supply to the distribution of prime numbers, the network algorithmically enforces a stable, mathematically bounded token economy. The function applies a gradient field to user voting power. As a user accumulates massive amounts of stake, their relative voting influence is logarithmically flattened. Fusing knot theory for flawless logic and Zeta economics for equitable influence creates a sovereign governance structure that cannot be bought, cannot be manipulated, or trapped in a paradox. This level of structural integrity allows DFT to expand its operational scope beyond planetary infrastructure, supporting high-latency, deep space logistics. To manage data across these distances, the system relies on the Infinite Digital Fabrics framework, a protocol engineered for universal, trustless interoperability. Under this framework, chain fusion smart contracts execute instantaneous atomic welds across completely heterogeneous blockchain states by projecting them both into the unified 14D manifold. The primary threat in interplanetary deployment is not bandwidth, but catastrophic physical breaks in high-latency network links. When a connection shatters, the network utilizes Ricci flow optimization to smooth irregular geometries over time. It automatically warps the metric to bypass damage. As it tightens, the data pathway is physically restored, rerouting critical information autonomously without human input. A continuous, self-healing 14-dimensional architecture is the only mathematically viable solution for maintaining autonomous interplanetary sovereignty. The 14-dimensional geometric unity manifold currently in operation is actually a transitional state, engineered for a specific mathematical upgrade path. The ultimate target for Web 4.0 is the 24-dimensional Leech lattice, a mathematical arrangement of spheres achieving an incredibly dense, highly symmetrical packing structure. Expanding to 24 dimensions folds the network into flawless symmetry, minimizing physical distance between data points. Operating within the Leech lattice unlocks the theoretical physical maximums for both data storage density and algorithmic error correction. Digital Fabrica Theory abandons the concept of a linear ledger. It transitions digital infrastructure into the physics of programmable matter. By enforcing fractal expansion, quantum lattice security, and topological governance, the framework delivers the uncompromising, infinite infrastructure required to secure the Web 4.0 horizon.